Hello everyone! Welcome back to the channel Bytes Busters. Today we are going to learn a very important topic in microcontroller. Today's topic is Microcontroller Instruction Set, Full Theory, 8051. In this video we will cover what is an instruction, what is an opcode, instruction length, 1 byte, 2 byte, 3 byte, instruction categories, addressing modes, examples of instructions, overview of the 111 instructions. This video will be very useful for students studying embedded systems, computer engineering, or electronics. What is an instruction? An instruction is a command given to the processor. It tells the CPU what operation must be performed. Examples of operations include moving data, performing arithmetic calculations, logical operations, controlling program flow. For example, MOV A R1. This instruction copies the value stored in register R1 into the accumulator A. Another example, add A R2. This instruction adds the value in R2 to the accumulator. So an instruction basically tells the CPU what operation to perform, what data to use, where the result should be stored. What is an instruction set? An instruction set is the complete collection of instructions that a processor can execute. Each processor architecture has its own instruction set. For example, the Intel 8051, the 8MEGA328P. Different processors have different instructions and capabilities. The 8051 instruction set contains 111 instructions and a total of 255 opcodes. These instructions allow the microcontroller to perform all necessary operations. Instruction format. Most instructions have two main parts: opcode plus operand. Opcode specifies the operation. Operand specifies the data or address used in the operation. Example, MOV A R1. Here, opcode equals MOV. Operands equals A and R1. This means move data from register R1 into the accumulator. What is an opcode? Opcode stands for operation code. It is the binary code that represents a particular instruction. When the CPU reads an instruction from memory, it first interprets the opcode to determine which operation must be executed. Instruction length. In the 8051 microcontroller, instructions can have different lengths depending on the operation and operands. The instruction length refers to the number of bytes required to store the instruction in memory. There are three types of instruction lengths: 1 byte instructions, 2 byte instructions, 3 byte instructions. 1 byte instructions. 1 byte instructions occupy only 1 byte of memory. These instructions usually operate on registers or the accumulator and do not require additional data. Example, INCA. This instruction increments the value stored in the accumulator by 1. Another example, NOP. NOP means no operation. The processor simply moves to the next instruction without performing any operation. 2 byte instructions. 2 byte instructions occupy 2 bytes in memory. The first byte contains the opcode, and the second byte contains an immediate value or address. Example, MOVA, #25H. Here, byte 1 opcode for MOV instruction. Byte 2 immediate data value, 25H. This instruction loads the value 25H into the accumulator. 3 byte instructions. 3 byte instructions occupy 3 bytes of memory. These instructions usually contain 16-bit addresses used for jumps or subroutine calls. Example, LJMP 2000H, meaning jump to memory address 2000H. Byte 1 opcode. Byte 2 low byte of address. Byte 3 high byte of address. Instruction categories. The 111 instructions in the 8051 can be divided into several categories based on their functionality. The major categories include data transfer instructions, arithmetic instructions, logical instructions, Boolean instructions, program branching instructions. Let's briefly examine each category. Data transfer instructions. Data transfer instructions move data between registers, memory locations, and input-output ports. MOV instruction. The most commonly used data transfer instruction in the 8051 is MOV. MOV simply means move data from source to destination. Example: MOV A, R2. Here the data in register R2 is copied into the accumulator. Immediate data transfer. We can also move immediate values directly into registers. Example: MOV A, hashtag 55H. The symbol hashtag indicates immediate data. So this instruction loads the value 55H directly into accumulator A. Memory to register transfer. We can also read data from memory. Example: MOV A, 30H. This instruction copies the value stored in RAM address 30H into the accumulator. Register to memory transfer. Data can also move between registers and RAM. Example: MOV 40H, R3. This instruction copies the value from register R3 into RAM location 40H. This is called direct addressing. MOVC instruction. Another important instruction is MOVC, which means move code memory. Example: MOVC A, at A plus DPTR. This instruction reads data from program memory and loads it into the accumulator. It is commonly used for lookup tables. Lookup table means a pre-stored list of values in program memory that the microcontroller can read when needed instead of calculating the value every time. In simple words, a lookup table equals stored answers. Microcontrollers often use lookup tables for mathematical functions, sine, cosine, log, 7-segment display patterns, character fonts for LCD, understanding the registers. In this instruction we have two registers. Accumulator, A, 8-bit register, used for arithmetic and data operations. DPTR, data pointer, 16-bit register, used to point to addresses in memory. So the instruction MOVC A at A plus DPTR means take the value inside A, add it to DPTR, use the result as an address in program memory, read the data from that address, store the data in accumulator A. Now a very common question students ask is, how does the microcontroller add A to DPTR? Because A is 8-bit and DPTR is 16-bit. Let's understand this step by step. First, remember the register sizes in the Intel 8051. Accumulator A is an 8-bit register. DPTR is a 16-bit register. DPTR is actually made of two registers, DPH high byte, DPL low byte. For example, DPH equals 30H, DPL equals 00H. So the full DPTR value becomes DPTR equals 3000H. Now suppose the accumulator contains A equals 02H. When the instruction executes MOVC A at A plus DPTR, the microcontroller performs this operation internally. Effective address equals DPTR plus A. But since A is only 8 bits, the processor adds A to the low byte of DPTR, which is DPL. So the addition becomes DPL equals 00H plus 02H equals 02H. Since there is no carry, the high byte DPH remains the same. So the final address becomes DPH, DPL equals 30H, 02H, which means the effective address is 3002H. Now the microcontroller goes to program memory location 3002H, reads the data stored there, and places that value inside the accumulator A. MOVX instruction. The MOVX instruction is used to access external memory. Example: MOVX A at DPTR. This reads data from external RAM into the accumulator. Example 2. MOVX at DPTR A. This writes data from the accumulator into external memory. Stack operations, push and pop. The 8051 also supports stack operations. Push instruction stores data into the stack. Example: push 30H. Pop instruction retrieves data from the stack. Example: pop 30H. Exchange instructions. The XCH instruction is used to exchange values. Example: XCH A, R5. This swaps the value of accumulator A and register R5. Another instruction is XCHD, which exchanges only the lower nibble of data. XCHD means exchange digit. It exchanges only the lower nibble, 4 bits, between accumulator A, RAM location pointed by R0 or R1. Important: only the lower 4 bits are exchanged, not the whole byte. Example: assume A equals 3CH, RAM 40H equals A5H, R0 equals 40H. Instruction: XCHDA at R05. Before execution. Accumulator: 3C equals 0011 1100. RAM: A5 equals 1010 0101. Lower nibble of A equals 1100. Lower nibble of RAM equals 0101. After execution, lower nibble exchange happens. Accumulator: 00110101 equals 35H. RAM: 1010 1100 equals ACH. Final values: A equals 35H. RAM 40H equals ACH. What are arithmetic instructions? Arithmetic instructions perform mathematical operations on registers, memory, or immediate values. They can change the value of A, accumulator, and may affect flags, like carry. The main arithmetic instructions are add C, sub B, INC, DEC, MUL, DIV. Now let's understand each instruction with examples. ADD instruction. First instruction is ADD. ADD means add 2 numbers. Syntax: add a source. This means the source value. ADD instruction. First instruction is ADD. ADD means add 2 numbers. Syntax: add a source. This means the source value is added to the accumulator and the result is stored in A. Example: MOVA, hashtag 10H. MOVR1, hashtag 20H. Add A, R1. First instruction loads 10H into the accumulator. Second instruction loads 20H into register R1. Then the ADD instruction adds the value of R1 to A. So the calculation becomes A equals 10H plus 20H. Result: A equals 30H. The result is stored in the accumulator. Add C instruction. The next instruction is ADDC, which means add with carry. Syntax: add CA, source. This instruction adds 3 values. Accumulator value, source value, carry flag. Example: MOVA, hashtag FFH. MOVR2, hashtag 02H. ATBC, add CA, R2. Accumulator contains FFH. Register R2 contains 02H. Carry flag is 1. Now the addition becomes FFH plus 02H plus 1. This equals 102H. Since accumulator is 8 bits, it stores only 02H, and the carry flag becomes 1. Sub B instruction. Next instruction is SUBB, which means subtract with borrow. Syntax: sub BA, source. This subtracts source and carry flag from accumulator. Example: MOVA, hashtag 25H. MOVR3, hashtag 10H. CLRC. Sub BA, R3. Accumulator equals 25H. Register R3 equals 10H. Carry flag equals 0. Calculation: 25H minus 10H minus 0. Result: A equals 15H. The result is stored in the accumulator. Inc instruction. Next instruction is inc, which means increment. It increases the value by 1. Syntax: inc register. Example: move A, Hashtag 0AH Inc. A. Accumulator initially contains 0AH. After executing Inc. instruction, A equals 0BH, so the value increases by 1. Important point. Inc. does not affect the carry flag. DEC instruction. DEC means decrement. It decreases the value by 1. Syntax. DC register. Example. MOV R0, hashtag 05H. DEC R0. Register R0 initially contains 05H. After executing DEC instruction, R0 equals 04H. The value decreases by 1. MUL instruction. Next instruction is mul AB, which performs multiplication. Syntax. Mulub. This instruction multiplies register A and register B. Example. MOV A, hashtag 05H. MOV B, hashtag 04H. Mulub. We multiply. 5 times 4 is equal to 20. 20 in hexadecimal is 14H. The result is stored in A and B together. A stores the high byte. B stores the low byte. Result. A equals 00H. B equals 14H. In assembly programming, sometimes we do not need to manipulate a whole byte. Instead, we may need to set, clear, or check a single bit. Logical instructions perform bit-level operations on data. These operations are very important in embedded systems when we need to set bits, clear bits, compare bits, or manipulate port values. The main logical instructions in the 8051 are ANL and operation, ORL or operation, XRL, exclusive or operation, CLR, clear operation, CPL, complement operation. Let's understand each instruction with examples. First, let's talk about the ANL instruction. ANL stands for logical and operation. It performs a bit-by-bit and between two values and stores the result in the destination. For example, MOV A, hashtag 0FH, MOV R0, hashtag 33H, ANL A, R0. Here, the value in the accumulator is 0F in hexadecimal, which in binary is 00001111. The value in register R0 is 33 in hexadecimal, which is 00110011 in binary. When we perform the AND operation, only the bits that are 1 in both numbers remain 1. So the result becomes 00000011, which is 03H. This result is stored in the accumulator. Next, let's look at the ORL instruction. ORL performs a logical or operation between two operands. Example, MOV A, hashtag 0FH, ORL A, hashtag 30H. In binary, 0F is 00001111 and 30 is 00110000. In AND or operation, if either bit is 1, the result becomes 1. So the result becomes 00111111, which is 3FH. This value is stored in the accumulator. Now let's understand the XRL instruction. XRL stands for exclusive or operation, also known as XOR. This operation sets a bit to 1 only if the two bits are different. Example, MOV A, hashtag 0FH, MOV R1, hashtag 33H, XRLA, R1. When we perform XOR between these values, the result becomes 00111100, which is 3CH. XOR is commonly used for bit toggling and simple encryption operations. Now let's look at the CLR instruction. CLR means clear, which sets a register or bit to 0. Example, CLR A. This instruction clears the accumulator, so the value of A becomes 00H. Another example is CLR C. This clears the carry flag and sets it to 0. You can also clear port bits such as CLR P1.0. This sets port 1 pin 0 to logic 0. Finally, let's talk about the CPL instruction. CPL means complement, which flips or toggles the bits. Example, MOVA, hashtag 55H. CPLA. In binary, 55H is 01010101. After the complement operation, it becomes 10101010, which is AAH. CPL can also be used with the carry flag. CPLC. If the carry flag is 0, it becomes 1. If it is 1, it becomes 0. To summarize, ANL performs the AND operation. ORL performs the OR operation. XRL performs the XOR operation. CLR clears a register or bit. CPL complements or toggles bits. For that purpose, the 8051 provides bit manipulation instructions. CTB, set bit, operation, set a bit to 1. Example, TBC, C equals carry flag. This instruction makes carry equals 1. Used to turn on an LED or send high signal. CLR, clear bit, operation, set a bit to 0. Example, CLRC, carry flag becomes 0. Before. C equals 1 after. C equals 0. Another example. CLR P1.0. Port 1 bit 0 becomes low, 0. Used to turn off an LED. CPL, complement bit, operation, toggle/invert the bit value. Example, CPLC. If carry equals 0 becomes 1. If carry equals 1 becomes 0. ORLC, bit operation, perform or operation between carry and another bit. Syntax. ORLC, bit example. ORLC, P3.2 operation. C equals C or P3.2 example values. C equals 0 P3.2 equals 1 result. C equals 0 or 1 is equal to 1 meaning carry becomes 1. Normally, a program runs line by line from top to bottom. But sometimes we need to jump to another part of the program, repeat a loop, or call a subroutine. That is where program control instructions are used. I will explain the following instructions. SJMP, LJMP, AJMP call RET DJNZ, JZJNZ. Let's start with the first instruction. Normally, a program runs line by line from top to bottom. But sometimes we need to jump to another part of the program, repeat a loop, or call a subroutine. That is where program control instructions are used. I will explain the following instructions. SJMP, LJMP, AJMP call RET DJNZ, JZJNZ. Let's start with the first instruction. First, SJMP, short jump. SJMP stands for short jump. It is used to jump to a location within -128 to +127 bytes from the current program counter. This means it can only jump a short distance, which is why it is called short jump. Next is LJMP, long jump. LJMP stands for long jump. This instruction allows the program to jump anywhere within the 64K program memory. Now let's look at AJMP, absolute jump. AJMP stands for absolute jump. This instruction jumps to an address within the same 2 kilobyte page of memory. Example, AJMP 1050H. It is smaller and faster than LJMP but has a limited range. So remember, SJMP, short distance AJMP, within a 2K page LJMP, anywhere in memory. Next instruction is call. Call is used to call a subroutine. A subroutine is a small program that performs a specific task, and it can be reused many times. Now let's talk about RET, return. RET means return from subroutine. After finishing the subroutine, RET tells the processor to return back to the instruction after call. So the sequence becomes main program, call, subroutine, RET, back to main program. This is how modular programming works in the 8051 microcontroller. Next is DJNZ, decrement and jump if not 0. This instruction is very useful for creating loops. DJNZ means first decrement the register value by 1, then check if the result is 0. If it is not 0, the program jumps to a specified label. Now let's see JZ, jump if 0. This instruction checks the accumulator value. If the accumulator A is equal to 0, the program jumps to a given label. Finally, JNZ, jump if not 0. This is the opposite of JZ. If the accumulator is not 0, the program jumps to the specified label. These instructions are very important for creating loops, conditional execution, and modular programs in the 8051 microcontroller. Addressing modes. Addressing modes define how the processor accesses data used by an instruction. The 8051 supports several addressing modes. The most important ones include immediate addressing, a register addressing, a direct addressing, indirect addressing, immediate addressing. In immediate addressing, the data value is provided directly in the instruction. Example: MOVA hashtag 20H. The value 20H is immediately loaded into the accumulator. Direct addressing. In direct addressing, the instruction directly specifies the memory address. Example: MOVA 30H. This loads data from memory location 30H into the accumulator. Register addressing. In register addressing, the operand is stored in a CPU register. Example: MOVA R1. This copies the data from register R1 into the accumulator. Indirect addressing. In indirect addressing, a register holds the address of the data. Example: MOVA at R0. Here register R0 contains the address where the data is stored. Alright guys, that's a complete overview of the 8051 microcontroller instruction set, from what instructions and opcodes are, to instruction length, categories, and addressing modes. If you enjoyed this video and learned something new, don't forget to hit the like button, share it with your friends, and subscribe to the channel so you don't miss our next videos. So make sure you hit that notification bell. Thank you so much for watching, and I'll see you in the next one. Keep learning and keep building amazing projects.